Okay, so thank you very much, Nelson, for the introduction, and thanks to the organizer for the possibility to present our work and, in general, the field in which I'm working right now. The work is, in some way, resuming this image. So we are trying to merge what you are doing, gravitational wave detection, with my field, which is cold atoms, cold trapped atoms, that is represented here with an iconic image, that of a BEC, the first Bose-Einstein condensate. We'll see later what it is, a macroscopic quantum state of atoms that have been achieved only 30 years ago, and that we plan to use in order to detect tiny ripples in the space-time, so gravitational waves. I will tell you more in these 3 hours. So here, a preview of what I will speak about in the next time. I will try to convince you that atoms could be a great tool to detect gravitational wave for a bunch of reasons that are listed here. So neutral atoms are all identical. We can take atoms here, atoms in another part of the world, atoms now, atoms tomorrow or yesterday, and they are all the same. So they are really good constant probe of several things. They have masses, so they can interact with gravity, for example. And since they have masses, they can be put along geodetics. Atom interferometry and metrology in general is a very good tool to track these atoms in free fall. And we'll use it in order to measure their motion, measure their acceleration, and measure then distance between different probes. Atoms, I will show, can be used in order to extend the sensitivity bandwidth of gravitational wave detectors based on optical means from, let's say, the 10 Hz and above to below. So the target bandwidth is what is called infrasound 1, which goes from, let's say, 10 millihertz to a few hertz. Other important things are that atoms can be used in a really tricky way in order to distinguish between the signal produced by gravitational wave and that produced by gravity gradient noise. That's really important if one wants to make a gravitational wave detector on ground. Gravity gradient noise is the fundamental limitation for optical interferometers based on Earth, like LIGO, for example. And we'll see a way to at least mitigate this problem. Last, with atoms, it's feasible to make single baseline detector, which could really save a lot of money, for example. And now I come to the real outline of these 3 hours. First of all, I will introduce atom interferometry, and most of all, the tools to make atom interferometry. These tools are cold and ultra cold atoms. I will spend quite some time to show you and introduce you to the field, so tell you how we really take atoms from room temperature, let's say under Kelvin, and go down to hundreds of picokelvin. Then I will tell you how we can put atoms on geodetics. That's really important if we want to go towards gravitational wave detection. Then I will show you how we can make atom optics elements. So take these atoms and we want to reflect them, we want to separate the wave function, recombine it in the same way as you do with photons. I will then show a lot of applications of atom interferometry, and then I will turn to the second part of the talk, that is the core one, that is gravitational wave detection with atom interferometry in the future, because we are not yet there. I will show measurement schemes and sensitivity. I will really spend some time on the sensitivity curve because it's quite strange, let's say. Then I will show how it's possible to reject gravity gradient noise using an array of atom interferometers. Important, as I said, for ground-based detectors. And then I will spend some time on the demonstrator for gravitational wave detection that we are realizing in France, not far from here, by the way. Last part, I don't know how much I will tell about it in terms of time finally, but it's other approaches of atomic physics for gravitational wave detection. I will extend in some way atom interferometry to atomic clocks. They're not so different from atom inertial sensors. Then I will show how it's possible to use even BECs, so really microscopic probes in principle, to see gravitational waves. And finally, I will give a few words on the use of metrological time and frequency optical links to transfer the stability of optical clocks along fiber networks. So let's start with a picture of an atom interferometer. What is an atom interferometer? So for a while, give it for granted that an atom can be represented as a wave. I will spend quite some time on it later. But if now an atom can be represented with a wave packet, and you know that quantum mechanics works with wave functions, so wave packets, it will have a wave function and a wavelength. So these represent my atom. Now, if it is a wave, it's intuitive that I can combine things in order to create an interferometer in the very same way as you do with photons. So you can find the right tool to split these atoms or this wave function in two parts. These two parts that will follow two different trajectories. And then I need another tool in order to deflect these two trajectories and put them together at the end of this configuration. And here I have to recombine them in order to see interference. So this wave function, it's split. And so if it's split, it means that the atom now at the same time follow this trajectory and this trajectory. So its amplitude will be along each one of the two 1/2. So this is the wave function along the two. Consider that this interferometer is placed in the vertical plane, like it is in this sheet of paper. So this is gravitational acceleration. So it's really climbing the vertical potential of this particle. What happens? The wavelength of the wave packet changes when it moves into the gravitational potential, and here we'll see later the lambda will be shorter. But what is most important now is that the two wave packet, two parts of the wave function, will have a different phase. So the part that travels along this direction has a different phase with respect to the other one. We'll see later how to control this phase. But now, if we see how is the possibility to find this single atom, I'm playing with one single atom, to find it here or there, I have to consider these two wave packets and see how they combine. For example, I see the probability to see the particle in output A. So I have, for example, that the relative phase here is 0. And now the two, they combine constructively, and I will find this wave function at the output A. Yeah. So I have a single particle. Here I split it. I have the one below, let's call it low. This one will do this, this, and here I split it again. It will be split in two parts. Wait, it will be more this. That's particle low. Okay? And then there is particle high. It's another color. Yeah. So particle up goes here. Here I deflect it. And then here I split it, also this one again. And one part will go here, and one part will go there. So now, if I plot... Exactly. And that's why I put the wavelength the same. We'll see later how the wavelength depends from the gravitational potential. So they have the same wavelength, and so they combine well in some way if you put them in the same direction. Okay?
It's not both particles, it's the particle.
Yeah. The two parts of the particles, yeah. I didn't put probability B, but it's exactly 1 minus probability A, because we have a single particle. And for example, here we have particle for sure on output A, and on output B, no particle. We don't find it. Vice versa, in this case. we'll see much later the schemes to detect a gravitational wave. The initial schemes, they tried to see how these two change in distance, so the separation change because of a traveling, a passing gravitational wave. But that's not really the way that people is thinking now. We'll have two interferometers and see a difference. Okay, so the two parts of wave function, they can combine to go out along port A or along port B, because the other one is dark, or with a given probability in both. For example, here, if we have a phase of pi over 2 between the two parts of the wave function, there will be exactly 50% probability to find the particle here, 50% there. So now, there are a lot of concepts in this slide that resumes 2/3 of what I will speak about later. So now, there is, for example, how one can associate a wavelength to matter, so describe matter in terms of waves. Second one, how is possible to observe interference. Third, how to design these atom optics elements, beam splitter and mirrors for particles. And last, how one can really find an interferometric phase. So I will discuss all these points in the following. So first of all, how is possible to associate a wavelength to a particle? So at the beginning of the last century, Einstein, in some way, found that photons can be described as particles. And de Broglie, 20 years later, was finding a way to reach sort of symmetry between photons and particles. So if photons, he was thinking, can be treated as particles, why not the vice versa, so particles treated like waves? And this is indeed what they tried to do in order to have a complete symmetry of this frame. So now, if we take energy and momentum relation for a photon, we have energy equal to h bar nu, and momentum energy divided by c, which is also h divided by lambda. That's for a photon. And so it is the most natural thing now that one could do, take the same relation for a particle and associate a wavelength. So you just recombine p equal to h over lambda, you put lambda, and lambda is equal to h over p for a photon, and you just assume that is the same for a particle. It was a sort of ansatz, let's say. But immediately after, Schrödinger wrote a wave function that is well known to everybody. It is a wave function, the basic one for quantum mechanics. So it's Schrödinger equation. And immediately after, a lot of experimental proofs, a lot of theory came out that was essentially based on this assumption. Now here I rewrote the relation of before, so lambda equal to h divided by p, just considering the relation between momentum and temperature. So the energy mp squared equal to 1/2 or 3/2 kBt, and I just reordered in order to have that the wavelength is equal to h bar, so the or h, the Planck constant, divided by the square root of 3 Boltzmann constant, mass and temperature. I want to focus on these two terms. So now, why don't we see interference phenomena with particles in the common world, so in our days? For example, why I cannot go there, taking the two rows at a time, and recombine the other side of the table? We can just make some math and just plug numbers. So if I take a Newman, let's say 80 kilos, and the temperature 300 Kelvin, plug the numbers here, and you find that lambda, our wavelength, is of the order of 10 to minus 24 meters. So difficult to see interference, so difficult to treat us as waves. If you go down in temperature and down in mass in order to raise this wavelength, you can consider, for example, a drop of liquid nitrogen, mass 1 gram, 1 millimeter size, for example, temperature 77 Kelvin, and you get up by a few orders of magnitude, but still you are far, far away from something that is reasonable. So consider that the atomic size is of the order of 10 to minus 10 meters. Okay, so here we are 10 to minus 21 meters. So we have to decrease the mass and decrease the temperature by a lot in order to hope to see interference phenomena. And the first real interference of matter waves has been seen right after de Broglie and Schrödinger wrote the equation with electrons. So in 1927, just 3 years after Schrödinger, 3 years after de Broglie introduced the relation between wavelength and to associate a wavelength to a particle, something has been seen. So they could see the wave function of electrons that confirm the wavelength could be associated to electrons, sending them in a metal. It's a really periodic structure, and you can see diffraction. So this is a wave function for an electron. And now I will show mass and associated wavelength of these particles. So here, for example, we have a mass that is 1 over 13,600 mu. And the lambda for an electron at 2 electron volts of the order of 1 nanometer. So 10 to minus 9 meters. So now we are considering size that are comparable with atomic interdistance. So they can the atomic mass unit. Yeah. 10 years later, they could see interference in an interferometer that looks like a Mach-Zehnder interferometer for photons, but with neutrons. So the mass now is much bigger, so 10,000 times bigger. The associated wavelength for neutrons that are thermal neutrons at 300 Kelvin is of the order of 0.1 nanometer, so 10 to minus 10 meters, it's fine. They had to wait 50 years more in order to make another step on the ladder, and in the 90s, thanks to cold atoms, it was possible to see interference phenomena with alkali atoms and biatomic molecules. Now we speak of 10 to 100 atomic units and associated wavelength of the order of the micrometer. That's really a critical point, because micrometer is the size of the wavelength of light. So you can use light. That's just a spoiler alert. We can use light to make atomic optics elements. From them, they'll really the rays speed up quite fast. A few years later, it was possible to find the evidence of Bose-Einstein condensate, 1995. So now we have a macroscopic quantum state that really demonstrate macroscopically. You can take pictures of BCs for an object that has 10 to the 6 atomic unit. Few years later with Fuller-N, so now we are. I didn't compute it. Lazy. Yeah. Fuller-N, and then a few years ago, really complex molecule. This is in the group of Arndt in Vienna, I think. So more than 10,000 AMU, and they are increasing. Okay. So now one ingredient is clear: decrease the temperature and, if possible, decrease the mass. And then another critical point to see interference is better than to see interference, to play with this wave function and to work on this wave object with the atom optics elements. Okay, is that the atom optic elements, they have to have in some way the size of this particle. So the size of this particle treated as waves is their lambda, so the de Broglie wavelength, and we have to build obstacles some way that have comparable size. Okay. If we go back to the human, 10 to minus 24 meters, we should make periodic structures of obstacles. A slit, for example, a 2-slit experiment of 10 to minus 24, but we cannot go through, okay? And it would be impossible. So we have to match the relative size. So if we take Bose-Einstein condensate, we'll see later how to obtain it, but it's a bunch of particles. At the beginning, they are thermal, so you start with particles at room temperature, or let's say a few Kelvin, and you go down. At the beginning, you have to treat them as particles that are like little balls. They go around, then you cool them down. Here there's a temperature, and you go down towards 0. What happens is that here is in the situation like the human one. So their associated wavelength is really much smaller than their size. But then, as you cool them down, wavelength increases, as we have seen before. And it increases at a certain point, their associated wavelength is bigger than the constant that you have for an atom. And this is the right condition to see single atom interferometry, the one that I showed before. Single atom and comes, you split it and you recombine. We are here, let's say at the microkelvin level for cold atoms. Then you can play more with temperature and you can go down, and what happens is that wavelength increases even more, and at a certain point it becomes comparable to the interdistance between the particle. And then the particles, they start to see each other, and these particles are bosons, okay? So they like to stay on the same mode. And if they like to stay on the same mode, at a certain point you don't distinguish them anymore because they are the same wave. And that's BC, okay? It's a macroscopic wave function where a lot of particles are exactly on the same internal state and external state. Is determined by the confining box. Yeah. 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 It's defined by the size of the box. And if you add one particle, it will just keep going down the fundamental state. This is the unique solution of the, or you increase the energy and then they can go out, can escape. If now we go in this condition here, so here the obstacle size is the interdistance between the atoms, okay? The reciprocal distance. If we stay here, how can we work like with optics with these waves? So we have to cool them down in such a way that their wavelength is of the order of 1 micron, okay? So optical light, and then we can use light beams in order to create periodic structure, and we can make separation, beam splitter, mirrors. We can make even multiple diffraction, like Bragg scattering and so on. So now I will concentrate on the first part of what I presented before, so producing these cold atoms. So go down from, let's say, room temperature to the best recorded temperature is, I think, 50 picokelvin. So atomic physics at the beginning of the 80s was a sort of a boring field. You, Nelson, can correct me because but so mostly everything was considered to be already known. And then at a certain point there was a really key discovery, key introduction in the field, that is the fact that you can use light to cool down the atoms, and you can cool down these atoms in a single step that I will now describe, from, let's say, room temperature to a few microkelvin, okay? And in terms of velocity, you can take particles at tens of meters per second, hundreds of meters per second, and bring them down to the centimeters per second or millimeters per second in, let's say, a few hundred milliseconds, okay? And then you have a really cold sample of atoms that you can use for a lot of things. So the field has been revived by this very wonderful introduction. And in 1997, these three guys, Steve Chu, Dalibard, and Bill Phillips, they got the Nobel Prize for laser cooling and atom trapping. And their discovery led in 1995 to Bose-Einstein condensate, something that has been foreseen 8 years before. And then 6 years later, it has been also awarded the Nobel Prize to Cornell, Weiman, and Ketterle. Other Nobel Prizes in the field are those given to study of coherence, laser-based spectroscopy, and comb generator, and in 2012 for the measuring and manipulation of individual quantum systems to Wineland and Aroche. Sorry. So now, how is possible to cool, also accelerate if you want, but we want to cool atoms using light? So when Bruce came 2 months ago to Bordeaux, finally, after a few hours, he concluded that it's really simple. And it was this part, laser cooling, no? Anyway, I will try to make my best not to make so difficult as I did it for him 2 months ago. um, and interrupt me if you have questions. So to understand laser cooling or Doppler cooling, you have to apply energy and momentum conservation principle. So we have a two-level system that is the easiest system you can imagine in atomic physics. So you have a system with just two levels. You forget all the rest. And these two levels are the ground and the excited state. And then you have a laser that is shined on this system. And this laser is at resonance. So it has really the right frequency to interact with these atoms. A few numbers. So photon energy is, as we said before, h nu. And I will refer most of the time to rubidium atoms because I'm working with rubidium atoms, and atomic physics, atom interferometry uses a lot these atoms, as a really nice line at 700 nanometer. It's roughly 1 micron. And so we refer to this line for quite a few slides. So this visible light, nearly near infrared light, has this energy 254 10 to minus 19 joule, or 1.59 electron volts. If you consider photon associated photon momentum, h bar k is this value here. And now what happens if at the beginning you have your atom there, so it's like a ball, but you represent with the two levels, and at a certain point you shine your laser on these atoms. At the beginning your atom is sitting here, okay? Red, it's red, like the level. You shine the laser, there is this photon approaching the atoms, this atom, single atom, and then there is a certain probability, a coefficient of Einstein, but it's not important, to make the transition, so the atom can just be promoted to the excited state, okay? So it changes its internal energy, and there is also the associated photon momentum, and so it gets a kick. That's a velocity, so this atom is not steady like the first one, but is moving by a tiny amount, 6 millimeters per second. That's the associated atomic recoil, okay? One photon here gives 6 millimeters per second to our atom. After some time, this is an excited state, you know, it decays. So it releases the photon randomly somewhere, for example, along this direction, and so you get an extra kick because releasing a kick, photon in that direction give a kick in the opposite one, recoil effect. And so you have to make the vectorial sum between this little arrow and this little arrow, and at the end of the day you have this velocity for the atom. Now take the same system, but slightly decrease the frequency of this photon. No, sorry, it's different case. Take the same laser, but now instead of taking a steady atom, give it a little velocity along this direction. So the direction along which the photon is coming, okay? So now the frequency of the photon is omega as before, so it's nominally right to promote the atom from ground to excited state. But what happens? There is Doppler effect in the system of reference of the atom. The frequency of the photon is moved above, because it's coming in this direction, by k scalar v. K is a wave vector and v is the velocity of the atoms. And then the photon just passes through. It's not absorbed because it's not resonant, okay? So here we have seen that if we take a laser at resonance, it's good at accelerating an atom, because we can go from an atom with zero velocity to an atom with a certain velocity, but an atom that is already cold, so at zero velocity, stays there. We want something more. So we can now take the laser and detune it, reduce its frequency a little bit, and what happens? We take the same atom as before, without velocity, zero velocity, and there is a photon incoming. The photon is not resonant, it has a certain detuning, so it passes through. The atom doesn't see it. In the second case, the atom moving towards the photon in its frame of reference, the frequency is moved upwards, and now the photon enters into resonance. And so there is a much higher probability to absorb this photon that comes against the velocity, and then the speed of the atom will be reduced by the photon momentum, 6 millimeters per second. And then photon is released randomly over the sphere. And then there is a, let's say, a random kick somewhere. Now, the trick is repeating this process a lot of time, because you start with atoms at 10 of meters per second or hundreds of meters per second, and you are removing every time 6 millimeters per second. Spontaneous emission, when you average over many cycles, doesn't give any effect, because it's just randomly distributed. So, but the atom do not have all the right velocity against the laser. So how to cope with that? Take that laser, put a mirror. So now you have two lasers, and the atom, either if it moves on the right or in the left, it finds the photons that cool him down. Okay? And then you can put another laser along this direction, retroreflected, and another laser along this direction, and you get this configuration. That's a molasse, an optical molasse. And so you have that an atom entering in the overlap region of these 6 beams is slow down whatever its velocity. If you consider the motion along one direction, here you have the velocity, and here you have the effective force. You have in dashed the interaction with the beam coming from one side and the beam coming from the other side. So an atom that has a positive velocity will mainly interact with the atom, with the photon coming against him. So, for example, if the atom is moving on the right, it will interact with the photon coming along this direction here. Okay, when it has the right velocity, it really interacts a lot. And you have the dashed one. An atom going in the other direction will mainly interact with the other beam, the beam coming from the left direction. Yep. Nuclear fusion, I would say no, absolutely not. It's used to, it's for neutral atoms here. For fusion, I don't know, but I would say no. You can
there's this thing where you take, for example, a pellet of some material, and you hit it with lasers from all sides, and the force compresses things. So that's a way of getting ignition, of igniting nuclear reaction, right? But here you're actually compressing something with
radiation pressure. Yeah, yeah.
So there are cross lasers in this case, but it's not functioning. These are gentle lasers, gradually slowing down the atom. This sort of ignition case is very powerful lasers crushing an object.
Yeah, you're really working on a 2-level system or few level system, so you really know which levels are in the game. Yeah. If you consider the action of the two, you make just the sum of these two dash profiles, you get this really nice dispersive shape that shows a friction force at the center. So an atom in this region will see a force that is linearly proportional to the velocity. Okay, a friction force. If you plug the numbers for rubidium, its mass, momentum, and the line width of the laser, we get an acceleration or deceleration, in this case, of 10 to the 4 g. It's quite strong. If you consider the 6 millimeters per second every time you interact, to go down from 100 meters per second to this level, you need 10 to the 5 interaction. Okay, so quite a lot. This is not enough to really produce a dense cold sample of atoms, because that's just friction force. You are not trapping the atoms. You have to find a way to confine them somewhere. Here, an atom entering this region will be slowed down to really almost zero, but at a certain point it will quit this region and will be lost. We want to collect the atoms. To collect the atoms, we have to create a central force. Okay, a center where the atoms try to go or want to go. To do it, we have to introduce new degrees of freedom, and the atoms are good too, because they have a lot of them. So, for example, we could play with the magnetic momentum. Atoms put in a magnetic field, they modify the energy level of their internal levels. And for example, if you consider an atom with a J0 in the fundamental state and J1 in the upper one, it means that here there are 3 different projections. So J1 is spin 1, and you can have projection 1, 0, and -1. That's the alignment, the relative alignment with respect to the magnetic field. So now we can create a magnetic field that is changing linearly in space, and you produce with simply two coils with the same but opposite current, and so you create a zero of the magnetic field at the center, and then the field is just growing, so it's negative here, goes to zero, and it becomes positive. You for sure learn Zeeman shift at university, and so this level, they get shifted by an amount that is proportional to the magnetic field, the local value of the magnetic field. So if you take M0 is not shifted at the first order. If you take M1 or -1, they are shifted on the opposite direction. That's really crucial because of this sign here on the two sides of the configuration. So now we can distinguish the atoms if they are on the right or on the left, because an atom here, see? Yeah. Yeah. An atom at the center of the configuration will have the three levels that generate. An atom a little bit on the right will have this splitting. An atom on the left, this splitting. But now, if the atom is on the right, the lower upper level will be the -1. If it is on the left, it will be +1. Okay? And now we can selectively interact with these two levels, because we can, instead of sending light unpolarized, we can choose the polarization. We can put sigma minus here. Sigma minus allows a transition from a value to that value's -1. So this light can only excite a transition from this level to this level, okay? But here is resonant, almost resonant. Here is out of resonance, okay? So this light will mainly interact with atoms here. This light, sigma plus, wants to make the transition from M0 to M+1. And here is on resonance. It's here. Here is completely out of resonance. So now we created a way to make the atom interact with the laser coming from the right side. Okay? And this gives exactly the same shape as before, but you have just to change the x-axis. Is not anymore velocity, but its position. Okay? So at the center, you have a central force. So an atom nearby will just be attracted at the center. In magneto-optical trap, the two effects work at the same time together. So that's really great. And then you have the effective total force is a friction force plus a central force. Yep. Continuously. They are continuously. Yeah, exactly. Yeah, yeah. So for example, you use it to observe the atoms. It's just scattered light, and you can just take picture of the atoms. We'll see later. You can measure a lot of things on with that light, because for example, you can make the atoms oscillate in the trap, and you can observe the modulation in this emitted light, and you can measure the trap frequency. Or so there are really a lot of other things that you can do with the. In principle, they will be too hot. Yeah, because you have to catch them in the. You have to slow down in order to. But then at the very end of the talk, I will speak about atom boxes a little bit. So there is a way to create a box, and then it's in a different context. It's a conservative potential, not one that uses scattering, but just conservative potential. I will introduce it later. But yes, in principle, you can make an atom box, and the atoms will just bounce on hard walls. Okay, so what you get finally is a temperature of the order of 100 microkelvin for, as usual, the rubidium atoms, limited by the line width of this transition, because if the atoms are in this region, they cannot distinguish. So now I put the lines bigger above, because there is an associated line width. So that's the probability to decay, and the time they stay there, and then they decay. And so what happens is that the laser, if it stays within a given amount of energy, is not distinguished if it is left or right, and that sets a limit of the achievable temperature in this way. Indeed, there are other techniques that allows to go down, but the problem is that the interaction, as it was mentioned before, with the atoms is quantized. You interact with one photon at a time. You absorb, you emit. You cannot interact with 1/10 of a photon or 1/100 of a photon. That is what you want to go below. I will not speak of polarization gradient cooling. That is, yes, the video are really. So that's a MOT done with strontium atoms this time at 461. So it's a blue light visible, and that's what happens. So the video is a little bit. So I put them here. So you see at the center of a vacuum cell a spot that as soon as you turn on, this is in real time, so I mean the time is not accelerated or slowed down, is what happens. You turn on the light and immediately you have a ball of something like 10 to the 9, few 10 to the 9 atoms at, in that case, 1 millikelvin. Yep. Yeah. Yeah. Oh. So to make an effective magnetic field with light, you have really to. It has been done, by the way, proposed by I think Salomon or some French in Paris. I don't remember. But anyway, it has been proposed and even tested. It works, but you need a lot of light in order to create an effective magnetic field. They call it instead of magneto-optic trap, they call it. I don't remember. There was a funny name, magnetic trap or something like. Yeah, it can be done. Yeah. Okay, so we are seeing this. So as I mentioned, to cool down atoms more, because 100 microkelvin is not at all good enough, is a good starting point that you can reach in, you have seen, few hundreds of milliseconds, and you get a lot of atoms there. But you have to go down much more. There is polarization gradient cooling. I will not speak about it, but it has also a limit. It goes down to, let's say, a few microkelvin. So you go down by 2 orders of magnitude, but not more. So in order to go down a lot and reach, for example, BEC, you have to use something else. You have to avoid the scattering of photons. Okay? So the quantic interaction with photons. To do it, you can use conservative potential. And you can create conservative potential with laser beams or with magnetic field. I will concentrate on optic beams. So if you shine a laser on atoms, what happens is that you perturb the atomic levels. So we have again the two-level system. Here is the unperturbed two-level system out of the laser beam. But as the atom enters in this laser beam, what happens is that if the laser beam is red tuned with respect to the transition, the ground level is shifted down and the upper level is shifted up. We don't care about it. We care about this one. You see now that the energy of the system here is lower with respect to there. So an atom is attracted by the high intensity regions of a beam detuned on the red of a transition. This is really wonderful because you can really make a cup for atoms. And it's easy to realize because you can take this laser, you put a lens, and you create a waist at a certain distance, like here, and you will create a three-dimensional trap for atoms. Okay? You can trap atoms there. So the trapping frequency will be really big along the two cross direction, while along the beam it will be really weak because the curvature is really low. But anyway, it works. You can combine two beams in order to have a tight confinement along 3 directions, or you can retroreflect this beam, and what you will have is a lattice, and you can create pancakes with a lot of atoms in each one, or even put one atom in each well of this optical lattice. You just write down the quantum mechanic formulation of the system atom plus electromagnetic field, and you find that there is, so it's Stark shift. Okay, electric Stark shift. And the shift is -1/2. Alpha is the polarizability E square. And so if you introduce an electric field, you shift up or down depending from the tuning. So this polarizability changes sign if you move the frequency above or below. So you can, now there are a few articles where they speak of atomic light shift engineering, because you can really make a nice trick with this kind of thing. So now we have seen how we can create a cup for atoms, and how to cool atoms in a cup. So take a coffee, and what happens? It spontaneously cools down by evaporation. How does it work, evaporation? There are two key ingredients. You have the removal of high energy particles. So it's something that takes away the particles with energy higher than the average of the distribution, and then there is a thermalization of the sample, of the remaining sample. The two can happen at the same time or at different times. For a coffee, they happen at the same time. So here particles are leaving liquid phase and they enter in the gas phase. Little wind just remove them. If you go in the Maxwell-Boltzmann distribution for the velocity, what happens is that these particles are above, let's say, 100 degrees. So they enter in the gas phase, they are removed. And then particle collisions in the liquid phase, they redistribute the energy. And so you continuously are going from this Maxwell-Boltzmann to this one, and you just reducing the average energy of the system. You can do the same trick with atoms. For example, you can put in an optical potential and how to evaporate the atoms. So how to select and bring away atoms that are more energetic. You just reduce slowly the depth of the potential. So here you let escape the high energy particle, and the remaining one, you have to do it slowly enough in order to allow collisions between the particles to recreate an equilibrium temperature at lower energy. You can do with a magnetic field with the so-called RF knife, so you can really select the particles at a given energy and just tilt the spin so they are just exposed from the potential. And that's the way that has been used to achieve Bose-Einstein condensate. So put them in a cap, put the atoms in some sort of conservative potential, and then lower the barrier or find a way to remove the high energy particle and allow interparticle collisions to reduce the temperature beyond the transition temperature. We can see here a cartoon of what happens. These are images taken of the atoms after a little while at different time along the sequence. So each image is a different sequence, is a new sequence stopped at a later time. And so you remove the trap and you let it expand a little, and you see that given by the temperature of the sample expands ballistically. So if the temperature is lower, temperature is going down here, after let's say 10 milliseconds, the size of the sample will be smaller and smaller and smaller. But at the beginning, it's always Gaussian, and that's what you expect if the sample is a Maxwell-Boltzmann distribution, normal distribution for temperature. At the end, you see this sharp feature that emerges that is not Gaussian, but is an inverse parabola, and this is what has been foreseen by Einstein and Bose, 1926, for the particle that enters this new phase. It's Bose-Einstein condensed phase, it's called nowadays. And it's where all the particles, they share exactly the same level. So if they share the same internal and external level, why do they expand? Because there is some residual expansion. It's the mean field energy. So all these particles, when you release, they interact, and so there is a residual energy. But okay, that's really technical. Immediately after achieving Bose-Einstein condensate by Cornell at Gila, the other group working hard to obtain it was second, but they obtained really great results, and so they show immediately that Bose-Einstein condensate could be really good to make atom interferometry, and they underline could. See later. So they realized two different BECs, one center there, one center here, and then they just released them. They expanded, and they could see immediately fringes. Okay, so they are good objects to see interference. Then 1995, so it's now more than 20 years. So there are really a lot of applications for BCs. So here I just put some. So they have been used to show that the flux is quantized and there is vortex nucleation. So they can see if they make the system turn, for example, with two lasers, they try to spin it instead of making it like a bag of water. Every time you bypass a given threshold, that is one quantum of flux, you get one vortex, and then you get 2 and 3 and so on. You can make an array of these vortexes. They interact. Okay. You can make BC on a chip nowadays, chip so big, and BC is let's say 10 microns, and they have been used to demonstrate really fundamental laws of quantum mechanics. For example, Einstein-Podolsky Rosen test very recently. They can be put, these BCs, in cavities. There is a beautiful environment to observe the interaction between atoms and photons at a quantum level. And they've been used, for example, to study self-ordering phenomena. Or they can be put on lattices in order to study, to implement quantum simulators. That's just a few, yep. And so the proofs is so one of the proof is the double structure at certain point. Here it starts to emerge. There is Gaussian. So if you fit with a Gaussian or two Gaussians, it doesn't fit well. The chi-square is starts to diverge. Okay. You can fit this distribution with a two-dimensional Gaussian cone shape. So that's a cloud of atoms. You send photons and you see the shadow. Okay, that's the signal. Okay, you see the shadow. It's some sort of negative of what you have. Okay. At the beginning, you have only a Gaussian shape. Take just one direction. You have a Gaussian shape here, for example. But if you wait long enough, so if you cool enough the system, you start not fitting well with a single Gaussian. You can put two Gaussians and you don't fit well because the central feature is not Gaussian, but it's an inverse parabola. So it really goes like an inverse parabola, and it's explained why. And that's one feature. Another feature is that if the BC has an ellipticity and you let it expand, it inverts the ellipticity just because of Heisenberg uncertainty principle. If you have something that is like this, you constrain more x here than there. That's a parabola because the potential is typically a parabola. What you said before. Yeah. And if you take a Maxwell-Boltzmann and you let it expand, because you convert velocity into position and you observe it. Okay, you make a time of flight. You obtain a Maxwell-Boltzmann. So these are two of the features. But then interference, for example, what I show, don't remember here. That's another proof that in certain condition you can make also interference with cold but not condensed atoms. But it can be proved with certainty. Okay, so in some configurations, a BC has a transition temperature of 100 nanokelvin. In terms of velocity, speed is a fraction of a millimeters per second, is not enough. This is a BC that is let expand. We will see later in a tower. And so you see that it is expanding with time. This I didn't put time because I didn't find it on the slide. It's not from me, it's from colleagues in Hanover. What they applied is a technique that has been introduced by Nelson 20 years ago. That is called delta key cooling. That is more delta key lensing, but what is it? So if you have a Gaussian potential with your cold ensemble sitting here and you release it, okay, you have the initial phase space for P and X, like this, for example. You let it expand, and what you have is that you convert the P extension, the P distribution, into an X distribution, a position distribution, because positive velocity, they goes on the right, negative velocity go on the left, and so you end up with this banana shape here. So you convert the p into x, and now you can apply a kick in order to turn that banana and put it on the x-axis, so that the final spread in the momentum space is much smaller than the initial one. What you pay is an increased spread in the space of positions. And how can you give this kick? So what they show in this paper is that the spread in momentum is proportional to what? P square. So the potential is Gaussian, so it is proportional to x squared. If you derive it along the position, the over the x of x squared is proportional to x, and so it's proportional to p. You just turn on for a little bit the initial potential after the right amount of time. So you give a little kick that so essentially the fast particle, they can reach this position, and you give a bigger kick, you slow them down more than particle at the center, to which you don't give any kick. And so you give the right kick at each particle, and what you end up is this configuration, and this is what you have. After the delta kick cooling, the object folds like a stone in some way, doesn't expand anymore. This is really important if one consider really long interrogation time. So here on Earth, we'll see we have, let's say, the second is more or less the limit, but there are proposals to put cold atoms in space. So more than proposals, now they are sent to the International Space Station, and so there one can in principle have really long interrogation time, 10 seconds, 100 seconds, limited by something more fundamental than the size of the drop. So now the point, how to put the atoms on geodetics. We want to go slowly towards gravitational wave detection with atoms. One way is really simple, just drop it. drop the atoms and they will be on a geodetic. You have to drop them on a vacuum tube, if not they will, so you have to produce them in a vacuum environment, if not they will collide with background gases. But dropping is a good way to put them on geodetics. You typically need long pipes, because if you drop something, it moves. And so a better way than dropping is typically launching from below in order to get a factor 2 in time for the free fall. And so it's what you can do easily if you take the magneto-optical cooling, so the beam used before to make a optical slowdown and trapping. So now instead of putting them like this as before, turn by 45 degrees, and you have this configuration here. So if the 4 beams, they have all the same frequency, you are cooling the atoms in a frame that is steady. But now if you shift downwards the frequency of the beam coming from above and upwards the beam coming from below, what you have is that you create a frame of reference moving at a definite speed where the atoms are cooled. So the atoms are not cooled anymore here, but they are cooled here. Okay, so it's just like an elevator, you're just shooting the atoms. So you can prepare the system here, and then you just switch the frequency, you shift them upwards and downwards, and the atoms just launch up. Just to give some numbers, the velocity is given by square root of 2 because of the configuration, the tuning divided by the wave vector. So for rubidium atoms, you take 1 meters per second. You can produce it with a 1 mega shift, something easy to do, with light at 1 micrometer. 1 meter per second is a flight, you can imagine the parabola. That's what we did when I was in Florence. I worked on a nano interferometry experiment to measure the gravitational constant, big G. And so what we had was a big source masses, a lot of cylinders on 2 layers, placed in 2 different configurations. So there was 1 measurement here, 1 measurement there. And 2 clouds of atoms were launched, 1 here and 1 there, in order to feel the existing gravitational field. So what do you have? You have a gravitational field of the Earth, small g, in both configuration. You have the gravity gradient. So between here and there, 30 centimeters in that case, you see a difference of 3 parts in 10 to minus 7, and you see it clearly because the sensitivity of these instruments is pretty high. But the gradient of planet Earth is the same here and there. And then you have the gravity gradient produced by these masses. So these masses source masses. In this configuration, they produce an effective force on these two atoms pointing like this. In the second configuration, they create a force, an effective force pointing like this. So if you make the difference between the measurement in the two configurations, you remove differentially the effect of the planet Earth, the bias, the gravity gradient of the Earth, and you remain with the effect of the masses. We measure big G with 10 to minus 3 accuracy, like Cavendish 300 years ago. Okay, but it's another method which is important to make to study systematics effect. And now they went down by 1 order of magnitude, so 10 to minus 4. So why I said all this? So here we had atoms along geodetics and two clouds at the same time flying in the vacuum pipe. So here there is time and vertical position for the clouds that we use there. Forget for a while this parabola. We had to launch two clouds, one at this height, one at this height, in rapid succession. So here the distance between one launch and the other is 90 milliseconds. For this cloud, we had quite a lot of time to load a decent atomic cloud. You've seen before, you need a few hundred milliseconds, let's say 1 second, to have a big atomic cloud. For the second one, you have only 80 milliseconds to load from the background. That's not enough to load enough atoms. We had just 10 to the 6 and not 10 to the 9. And then the system is not good. So what we did was to, at the very beginning, we load what we call the cloud 0. We load it here, big cloud. We store it along the geodetic, throw it up, is this one. Meanwhile, we loaded the second cloud, the cloud 1. Right before cloud 0 came down here, we launch cloud 1, we recapture the other one, we prepare and we launch it, okay? So you can really play along geodetics in this way. Dilute gases, they are really dilute. So you can make calculations 10 to the few 10 to the 9 atoms over a few centimeter cubes. They don't interact. So there is an experiment called Kurt Gibble US, somewhere I don't remember, is working with atomic clocks, fountain clocks, season clocks. And so to measure this effect, he was launching hundreds of clouds in rapid succession, and so they were colliding all along the way, and they measure the shift given by atomic collision. It's really small, but if you make an atomic clock, you want to know it. And it exists, by the way. Yeah. So before I said that condensate, they could be good for atom interferometry. Indeed, they are good because you use them as a source of really cold atoms, collimated with the delta key cooling, but you don't use BEC by itself because of the inverted parabola that's given by the mean energy, and it's not easy to control it, okay? And so you want to avoid the collisions between the atoms collapsing this unique level. And so what you do typically, you prepare a BEC, you let it expand a little bit, and you apply delta key cooling. So you avoid collisions. I don't know if I respond to you. No, clearly not. Okay, colleagues in Stanford, they did a bigger version of an atomic fountain, because that one is an atomic fountain, that is represented in sketch here. And so they have you can see a little bit different parts. We have an atomic source here, 2D model and 3D model, just technical details. But anyway, here you produce the atoms and you can launch them up. They can also produce atoms here and drop them. There is the interferometric region is where the atoms fly in the in free fall along the geodetic, and you have to shield that region as much as possible, because any magnetic field, electric field, whatever, perturbs what you want to do. And so they adopted 3 layers magnetic shields, and they define very well magnetic field inside. And then here there is some optics to prepare the system to launch the atom upwards. It is more complex than what we do, and better than what we do. We did. And then there is a final part here, rotation compensation system, that is what? So if you take planet Earth, there is their fountain is in same for something like this. It's turning, okay? And so while they make their sequence, the fountain is just rotating, and they can clearly see Coriolis, okay? And so what they are doing with this rotation compensation system, they are, so while it's rotating, they are shifting a little bit for that second and a half, 2 seconds that they made the experiment, they are tilting the beam in order to keep it along a given direction in space, if you don't consider the rotation of Earth, okay? So you subtract the rotation of Earth in that way. And what did they do? So they could launch the atoms with a moving lattice, something more complex than what we do, but I did not explain. They launch them upwards till the top, so 10 meters. You can calculate is roughly 1.4 seconds to go from here to there, and another 1.4 seconds to go down. And then what they did, when the atoms came down, they could just bounce them, okay? So they can in some way prolong the free fall on a new parabola, okay, in a consistent way. And that way they could show that they can make 5 seconds, and which is more than 2.9 that you can achieve by simply doing one parabola, okay, of free fall. The second way to put atoms along geodetics is to put not only the atoms but the entire lab in free fall. And there are different ways to do that. Colleagues in Bremen and Hanover, is always Ernst Russell does this. They have the use of the drop tower in Bremen. So they have a tower of 146 meters, which means 9 seconds of free fall if you launch, 4.5 if you drop, and a residual gravity uncertainty, so you are close to free fall at 10 to minus 6 g. They extended their work with something flying for 5 minutes with a rocket. So they launched a rocket with BC inside. They did atom interferometry really recently, and there they have 5 minutes of free flight, and 10 to minus 5 g turbulence of the high atmosphere plays a role. We in Bordeaux are playing with an airplane that does a parabolic flight, 22 seconds of free fall and 10 to minus g. It's not very good in terms of residual acceleration, but it's fun. And then I will show you later. I did it once. So we have study mission to put atom interferometers or atoms along geodetics on a satellite. That would be the perfect environment, really quiet, and you can stay for as much as you want, let's say. And the environment is really good, better than 10 to minus 6. And really recently they launched an experiment on the International Space Station. Result will be probably next year. They also have a mission of 3 years. It's called CAL, or Cold Atomic Laboratory, and they will have an environment that is not so good as a satellite because ISS is moving, bouncing, they are aligning and so on. People is there. And so now I show a couple of movies. One of the drop tower, so I took them from their side. So we'll see what happens along the vessel that flies along the I have to go on the desktop because it doesn't work. So there it is. So we are at the top of the vessel, goes up to the top and then it falls down. At the bottom, it falls. It's recut in some way. Yeah, okay. Here you see at certain point it reaches the top. It's slowing down. Inversion. It's the top of the tower. When it goes down, there is foam that is placed. So the system is launched. Okay, it's launched here, and then at the bottom here they insert this recapture system in order not to destroy the experiment. It costs quite a lot, and it has to survive 50 G. Okay, obviously they have to evacuate the entire tower. The landing. Landing is probably a little bit gentler. Catapult. They can also drop it, but they have 1/2 of the time, and the same 50 G shock. So they have 10 seconds. That's in real time, the sequence. They have to evacuate the tower. It's huge, to 10 to minus 6, I think. And then, as inside this foam and the recapture, they have to lose because they have to re-prepare the system, and so they go to normal pressure and they have to re-evacuate, and so finally they have 2-3 shots a day. And then I show, so next slide, it's what do just like this. It's what we do down in Bordeaux on the 0G plane. So you can imagine what it does. So the plane reaches almost 60 degrees. Already the 2G phase, because it's accelerating upwards, is really strange. It's really uncommon and unnatural. And then the 0G phase, the first parabola, I wanted to pay to exit the plane, but yeah, 22 seconds of free fall. And then with the second one, I would have paid to stay on. And anyway, 31 parabolas every time you go on, because they don't stop the plane for you. And so 55 degrees, and yeah, it's great. And the experiment is falling with you. It's falling with the plane, and yeah, it's quite an experience. Yeah. So, okay, so there is a third way to put the atoms in free along geodetics, and it is to, in some way, is closer to what you do with LIGO and Virgo. So it's load these atoms in a lattice, produce with a mirror in free fall in some way. So, or with a suspension, so free fall in a given bandwidth, or free fall because it's in a drag free, so in a satellite. That's an interesting method if one wants to make cold atoms in space and gravitational wave detection in space. One can make the free fall there, which transfer it to the atoms. Okay. Now we go to the atom optics part. So we go back to the scheme of before, and we want to see how we can produce this manipulation beam that can split, deflect, and overlap the wave function again. Okay. So we go back to the two-level system here, state 1, state 2, and we have a laser that couples the two levels. A laser at resonance. What happens when you start with the atoms in the low level and you turn on the light? The laser excites Rabi oscillation. You did it for sure in quantum mechanics a few years ago, or yeah. So here there is atomic population of state 1. Here at the beginning is 1. So the population of state 2 is a single atom. We are doing everything with one single atom now. And then the population is just swinging back and forth between 1 and 2. Okay? So after a certain while, you find the atom for sure in state 2, and then again in state 1, and then in state 2, and so on. You understand the game? You stop the laser at the right time, for example here, and you have that the population are inverted. So now the atom is not anymore here, but is on state 2. That is a mirror. It's not evident now, but it will be in a while. It's also called pi pulse. You can stop it 1/2 of this time. So here, and here is clear what you have is a coherent superposition of the two levels. So the atom is not here, is not there, but it's on both. Okay, 50% here, 50% there. You get the whole picture if you consider momentum conservation. As we said before, photons carry momentum, and so when the atom is promoted to level 2, it not only changes the internal state, but changes also its momentum. And so the atoms that was traveling along this direction gets kicked, and so you see why it's a mirror. The atom that was traveling along one direction now is split, because so one part is deflected, one part continues on its path. This is a beam splitter, okay? And now you can combine these elements to make a full atom interferometry. Beam splitter, mirror that act at the same time on the two, and final beam splitter. So the probability to find this single atom at output 1 results to be an oscillatory function of the external potential. So if you repeat, so for example, if now the atom goes out there, and you, again, the interferometer is on the vertical plane, so it's a gravimeter, and you extend it a little bit more so that this line is a little bit above, you will shift some population on the other state. Okay, so you can just changing the height is like what they did with the neutron interferometer. They were just changing the angle, and they were just changing the effect of gravity and going from one part to the other. And it's also a function of the phase of the manipulation beams. One can write the full formalism in terms of path integral mathematics, and you find out that this phase that you obtain at the end is a function of the phase of this laser that is used as a sort of ruler for these two trajectories in different positions, A, B, C, and D. Okay, so you get that the phase, so in path integral formalism, the phase at the end is given by the phase that you accumulate along one path minus the phase along the other path here, with certain rules to pick up the phase. So for example, when you shift the momentum upwards, you get a positive phase of the laser imprinted on the atoms. When you go down, you get negative rules. Just forget them for now. And so you get this. If you write the phase above minus the phase below in terms of the four interesting points, you get this: phi A minus phi B minus phi C minus phi D. You can reorder the terms, and you get that this final phase is equal to phase here plus the phase there minus twice the phase at the center. That's really intriguing in some way, because it turns out that the phase that you measure in an atom interferometer is the phase along 3 points that are the classical trajectory of the atom that follows the mid path, and this is called the mid path theorem. And it works really well for a simple reason. So far, all the measurements have been done with a potential that has shown at most the second derivative of the potential, so the curvature, let's say. So the gradient of gravity, okay? So if you go from here to there, you get the same difference as you go from here to there with opposite sign. So half the sum of this is twice the center. If you split much more this wave function, you start getting effect of the curvature or the next derivative of the potential, and then it will not work anymore. Anyway, so now suppose that you fix all the parameters. You are measuring a given output here, for example, for the two ports. And then what can you do? You can move the last laser, the phase of the last pulse, in order to scan in a controlled way the fringe. So you can move it in every repetition of the experiment. You move it by a tiny bit, you change it, and you get a fringe. But you can also stop where at the maximum of the sensitivity, so the maximum slope, you can stop there. So you tune the phase of this one at the right position, and then what happens is that you are observing the phase stability. So if nothing else changes, the phase stability of this beam. That's, alert spoiler again, that's the way finally that you observe gravitational waves. Okay. Is interacting only here, then you turn it off. Free propagation of the two parts of the wave function. You turn it on here, and then off, and then on again there. And you can control the phase of these pulses. Yeah, so there are 3 pulses. You turn it on here, here, and here in time. 3 pulses, equally spaced. Okay. So now we got again the 2-level system here, and so far we consider direct transition, that for rubidium is a microwave photon, 6.8 gigahertz, and we get this interferometer is half covered there with small area, so a small separation between the two paths. So if you want to increase the sensitivity to the fact that you want to measure, for example, gravity or whatever else, you want to increase this area as much as possible, because you are linearly sensitive, so your sensitivity scales linearly with this area, which means with the splitting of these two wave part of the wave function. And how can you increase by order of magnitude easily this interferometer? So you can, instead of using the microwave photon to go from 1 to 2, photon at 6.8 gigahertz, you can use an upper level, the one of again 780 nanometers, so an optical transition, almost optical transition, and yes, you put some detuning because you don't want to promote the atoms there, but just use this level as a support to make a Raman transition. Okay, so now you have two photons in the game, and these two photons are shined with two lasers counter-propagating. It's represented here, one from below, one from above. Okay, now the atoms here that get deflected absorb one photon from here, and so you get the kick upwards, this photon, and then it emits the second photon along this field, and so it emits it downwards, and you get a second kick upwards. Okay, and so now instead of having a kick given by a microwave photon, you get a double optical kick. Okay, so you scale up from 6.8 gigahertz to twice 380 terahertz, so 10 to the 5 times. Wavelength of the photons goes from 10 centimeter to 1 micrometer. Is the same scaling as there. That's great to increase the sensitivity of the interferometer, clearly, but there is still a problem with Raman atom interferometry. That's the fact that the atoms at every single time during the interferometer is on the two paths on different internal state. And so, for example, if there is electric field, magnetic field, whatsoever that influences the two levels here in a different way, you collect some systematic effect. A little bit is mitigated by the fact that the atoms spend one half in one state and one half in the other one. And so the one with the momentum is the same, but it's not completely removed. A nice way to get rid of this problem is to eliminate this level and just make a Bragg transition on the same level. Obviously, you have different internal state. So you have an atom with a given velocity and you reflect, for example. And so you have that the two levels, this one and that one, they are the same for the internal state. So it's one and one there, but they are different for an external degree of freedom. And that's fine. And now all the fact that could give a signal because of different internal state, they are removed, completely removed. And here we come to an atom interferometer. So full description, let's say. Preparation stage, magnetic optical trapping. You produce 10 to 9, few 10 to 9 atoms at a few tens of microkelvin. You launch them, you put them on geodetics. You further select the atoms. It's represented here. You select the right atom with the right internal, external degrees of freedom. You put them in the correct state. And then they're ready to enter the interferometric region where you apply the pulses. The pulses are applied with the external lasers. In between, there is free propagation of the atomic wave function. And at the end, the atom exits the 2 or more output ports. And you have to count the atoms on each of the output ports. And you do it with a fluorescence detection. So you just shine resonant photons and you see if the atoms are here or there, and you count. I put some numbers. So yeah, so that's an atomic interferometer using a thermal atoms, not BC. So we have the Bertoldi wavelength of the order of the micrometer, which is visible light, good to interact with it. Temperature is of the order of the microkelvin, so 1 centimeter per second, and the path separation, distance between here and there, is of the order of the millimeter. Yep.
Just go back to that slide for just a second. I want to ask a question.
This one?
Right. So eventually you're going to build a gravity detector by letting the gravitational wave modulate the phase of one of your lasers. And you've explained how as you shift through one fringe here, you go from all the atoms going out the top to all the atoms going out the bottom and back.
Mm-hmm.
But now here the number of atoms is 10 to the 5 or 10 to the 6, and the square root of that is 10 to the 3. So you can't here detect sort of less than a 10 to the minus 3 of phase.
The phase with the interferometers nowadays, let's say the standard interferometer, like what we are doing with our underground detector, you see later, is 10 to minus 3 radians, okay, 1 milliradian. Then you can use more pushed techniques in order to go down, and you can consider to go down to 10 to minus 5, 10 to minus 6, using more atoms, squeezing, large momentum splitting. I will come to that later. Yeah. So there are a lot of applications for atom interferometry, measurement of inertial forces, measurement of fundamental constants. You already spoke of G, h bar over m, testing general relativity like weak equivalence principle, post-Newtonian gravity, a lot of other bunch of quantum tests and tests of matter neutrality, interferometry with antimatter, and so on. So the list is long. I will now focus on a few examples. So the first one is an atomic gravimeter. So consider again the same picture of before, and now we can calculate intuitively what's the phase at the output, considering the phase of the laser at the 4 different points. Consider the laser stable in time, the wave front of the laser stable. So we define 0 the phase here. Then the atom, so the atom climbs the potential with just parabolic motion, shift by the momentum transfer with the manipulation. So we can follow this parabola, and we get that the phase in B, for example, is given by V0, that is the vertical velocity of the black line here, plus momentum taken from the photon kick here, plus 1/2 gt squared. That's just the parabolic motion. The phase in chi, it's easier because we don't have the momentum kick, so it's just the parabolic motion on the black here. And the phi in D is, I don't remember which one of the two. I took the mid-path line here, so I consider half kick. So instead of, yes, h bar k over m over 2, so half parabolic motion here, and I get this phase for D. I apply the rule that I found before, and I get that the phase that I measure is k, the wave vector of the light, g t squared. And so you see immediately that you measure the phase, you know the timing of the pulses, you know the wave vector of the light that you are using to manipulate the atoms, and you can get g. And you can get g if you plug the numbers with quite some sensitivity. So you can get the signal in phase given by gravity is 1.6 10 to the 8 radians, and as Bruce said before, we can measure it with 10 to minus 3.
I think I've understood one thing I was really confused by. So the half of the atom that goes along one trajectory, the half that go along the other half, they're both climbing up with the same amount of gravitational potential. But you still get a phase shift here, which contains g, because they're going at different velocities.
And you can see it intuitively because you have, so consider one trajectory and the other one separately. Okay, so now you have that you have this wave function, okay, with a given wavelength, and consider these two lines horizontal and this one climbing. Okay, so when the wave function climbs, it slows down. Okay, it doesn't slow down. Less velocity, less temperature, it increases the wavelength. Okay, that's why it is longer. But this one is common mode if this one is horizontal. Okay, this one is common mode. But these two parts, they are at different height. Okay. Yeah. Yeah, you can see also with math, but intuitively you just see that the horizontal part is done by the two parts of the wave function at a different height. The two other is common mode because it's the same trajectory in some way, if you see it as a square. But the other two, one is below, higher, so shorter wavelength, and the upper one is longer wavelength, and so you get a neat phase. Yeah. 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 Then it's not so clean because it's not horizontal. But okay. Yeah. You can plug the numbers also for taking that on something that rotates, and you get sensitivity to rotation. Okay. I have 10 minutes more probably, or not? It's finished. There is nobody. cansato mi 7, 17, just 10 minutes. It's fine. Okay. So this is a gravimeter. It's 7, no? Yeah. Okay, it's good. So that's a gravimeter realized by Steve Chu almost 20 years ago. So they measure gravity with a sensitivity of 3 × 10⁻⁹, and so they could see clearly tides. One problem with gravimeters is that you are measuring gravity in this position using a ruler. Yeah, I did it really quick. So here you have time, and here you have to measure gravity. So you take, they are measuring this, essentially they are just measuring g, okay, the acceleration, and they plot it versus time. So they keep repeating, launching clouds for days, okay, and they see the tidal, oh, that's delta g, so the residual acceleration, that's, yeah, few days probably. Noon, yeah. The tidal signals, yeah. Yeah, sorry, I did it. Yeah, no, I was too fast. The problem with gravimeter is that you are measuring gravity using a ruler, okay? So you are measuring essentially free fall of this cloud with this ruler done with an optical lattice. That is a laser retroreflected on a mirror. Now, if the mirror shakes, your ruler is shaking, and you get an effect. You get noise, okay? And the effect is visible here. Instead of having the nice parabola, signal that I plot before, you get this kind of signal, okay? You can still feed a sine, but it starts to become quite hard. You have contrast, okay? So you see that every time you get a different population on the two parts, but not as you scan the phase. It's not consistent. That's because there is an extra signal that you cannot control, given by the motion of this mirror. You can stabilize it and you improve it, but at a certain point you are limited on ground by the motion of this mirror. Colleagues at CIET demonstrated with a portable gravimeter that if you have a better environment, you have a better signal, and so that's the signal. They measure the Allen deviation for the gravity signal measured in Paris, and that's the signal they measure in the underground lab where we will do our demonstrator. So it's one order of magnitude better in terms of sensitivity. One solution that moves towards gravitational wave detection is to use not a single cloud, but two clouds of photons. Okay, so now, as we did, for example, for big G, so you have one cloud here, one cloud there. So gravity here is gravity of Earth at this position, plus the noise of the mirror. Gravity there is gravity of the Earth here, plus gravity gradient of the Earth multiplied by the vertical separation of the two clouds, plus this noise. When you make difference, you remove the noise differentially. You don't really make difference, but you just have one fringe, the other fringe that looks really bad, but then when you plot one against the other in a Lissajous figure, you obtain this ellipse. Okay, so the points are just scattered, so in time they arrive randomly in different position, but with time they design an ellipse. The ellipticity of that ellipse gives you this term, so the gravity gradient, okay, between the two. So there is a way to remove the noise of the mirror, so vibration, you can completely remove them to get the gravity gradient between the two clouds. If you increase the distance, there is a time delay that messes up things and makes it not feasible anymore. We'll see later. You can use more than two clouds, and you can measure not only the gradient of gravity, but you can measure the curvature. In my previous experiment here, 3 clouds, curvature. And what they did in Stanford was to measure the curvature not with 3 clouds and just making the sum of the 2 minus twice the value here, but they measure the effect of the curvature on a single wave packet. So what they did was to launch one atom, and they split it so much they could see the effect of tidal force on a single wave packet. That's really important from a fundamental point of view because they measure something that is invariant in general relativity. So the curvature is something related to metric, okay? And is measured with a single quantum object. Airborne atom interferometry, said before, rocket plane on International Space Station, proposes to go on a satellite on Earth, longer and longer instrument. So the Stanford Fountain, 10 meters, Wuhan, I think is 12. Hanover is also building a big vertical instrument. We are doing one underground, horizontal, 150 meters probably. And now we reach the important part, probably we can shift it to tomorrow, that is atom interferometry and gravitational wave detection. So now we go to the core of the presentation, but we do it tomorrow probably. Yeah. Questions or? Yeah, that's a good question. So, okay, take this one, for example. So, if you go here, the answer is really clear. So there is no excited state. They're just two different external states, but the same ground state. If you use a Raman atom interferometry, that's a metastable state. It lasts for, I didn't calculate it, so I calculated during my PhD, I don't remember. I think that Bruce did the same question 2 months ago. I did then recalculate meanwhile, but I think it was weeks, something like this. So yes, it's not the fundamental, but it's a metastable state. So there is no problem. In a scheme that we will see tomorrow, using optical transition, you put atoms on a really excited state that has a lifetime of 160 seconds. Seems safe if you make a 1 second interrogation time, but if you want to go to space and make a 100 second, it's not safe at all. But there is a way to go beyond that. We'll see tomorrow. Yeah. Yeah.
Is this the best measurement of G?
So I did the first one at 10 to minus 2. You mean all measurements of big G? So I did 10 to minus 2, so it was worse than Cavendish. I did 10 to minus 3. 2 years ago, my previous colleagues, they did 10 to minus 4, few 10 to minus 4, let's say. Now they have a proposal to go to 10 to minus 5. The standard way of measuring big G is not with free-falling quantum probes, but is with suspended masses, and measuring, for example, a torsion with a pendulum or with a balance. So it's a completely different way, so it's good to make a... And the sensitivity they claim goes to 10 minus 5, even below sometimes.
I have a really stupid question. There's measurements of big G, Newton's constant.
You said big G, no?
And there's measurements of little G, just the acceleration.
My question was little G.
Oh, sorry.
No, but
Sorry, I wasn't big G.
so the point is, you were showing things that were measuring 10 to the minus 9, right? 10 to the minus, and this is measurements of the acceleration of gravity at the surface of the Earth. And so you lift your gravimeter up even a few centimeters and you see it, the difference, right?
Yeah, so...
But then the measurement of big G is much harder.
Yeah.
Right? Because then you actually need to take two masses in the laboratory, because we don't know how much the Earth weighs, right? That's the problem.
Yeah.
Cavendish's first paper was about weighing the Earth.
Yeah, you can invert the... Yeah.
So you're asking about little G, not the
So to answer to little G, is not the best. So if you use squids, for example, I think that they go 2 or 3 orders down, but they're not absolute, so they drift with time. So periodically they need to tune them, and they tune them with an atom gravimeter, for example, because an atom gravimeter, you're measuring small g, rotation, or whatever, with respect to the spacing of 2 levels, okay? It's like an atomic clock. You have a spacing of 2 levels, and you measure time in terms of the frequency. separation of the two levels. So it's absolute. It doesn't change with time. It's not the best, but it's absolute. Yeah.